I'm Lucy, and I'm an engineer at Uber in Denmark. We have about 140 people out there, and we build most or nearly all of the platform that engineers across the world at Uber use day to day. So that's both stateless and stateful infrastructure, and we also do a lot of the work around Uber Eats, and we're all based in Aarhus, which is about 4 hours by train from here on Deutsche Bahn, maybe 6, but you know, yeah. And the scale, but because we're responsible for the entire platform, the scale can get pretty big. So we, in my team in particular, run a stateless compute platform called the Up platform, and we run a lot of stuff nowadays. So the Up platform is a global control plane for stateless services. We have 5,300 services. We have over 3 million CPU cores now. That's why I updated the title, because when I walked in today, when I submitted this, it was 2.9. When I came in today and looked at the number, it's 3.1. So, yeah, so the Up platform has a lot of workloads running on it, but it also has a lot of changes. We're big believers in automation of process with no human in the loops. We have 34,000 weekly production deploys, mainly because we have a lot of continuous deployment of services. This is spread out over a few dozen Kubernetes clusters for resiliency purposes. And the way Up works is it's a federated goal state-based system. So service owners define to us what they want their service to be shaped like in terms of how many containers they need, what regions they want to be placed in, and dependencies like this. And then we evaluate that at the time they request it and place them on clusters based on the goal state they've asked for. They might ask us for goal state in more abstract and simple terms, and then we condense that down into specific decisions. And that's an intentional choice because it means it gives us a lot of flexibility about how we place these services. We decided to migrate to Kubernetes before we were using the system called Peloton. Peloton came about because back when we built it, Kubernetes was very much in its infancy. There was a blog post about how with a lot of hacks, you could maybe get Kubernetes to run 1,000 nodes in a cluster. That it was not enough for our scale at the time. We had about 10,000. So we built Peloton. It was built on Mesos. And you could almost think of it as like a basic version of Kubernetes. It has workload execution. It has optimal evaluation of tasks, but because it was built on Mesos and because it was proprietary, we found it becoming increasingly difficult to operate with. Mesos obviously was becoming less and less maintained as well because everyone else was moving, which meant that we were not able to do things that we previously were. The maintainers were becoming quite unresponsive to us, and Peloton itself was taking up a lot of our resources because we were the sole main users of Peloton, despite it being open source. So we had to put all of the effort in, and we thought at that point, well, Kubernetes has run rings around us and our system, so if you can't beat them, join them. And so we decided to move over we decided to move over and hopefully get some of these features to improve our platform with. So in order to move, though, there's a few things that we needed. The first thing is that migrations must be touchless. What I mean by this is that service owners shouldn't have to do anything to move from Peloton to Kubernetes, because if we had to ask 5,600 stakeholders to please do something, we will never get there. So that's the first thing. Also, we can't have downtime. We can't just turn the Uber app off for a day while we move everything. And we can't do leaps of faith. We can't just shift everyone onto Kubernetes and just hope for the best. It would cause a lot of disruption and cost a lot of money. And the other thing is, going back to that leap of faith, we didn't want to do just one big migration. Everyone's on Peloton one day, everyone's on Kubernetes the next day, because the risk of that jump is huge, because there's no way you can personally work out all of the risks of moving for all of these services and all of these interlocking dependencies and just move them all at once. So we had to have a system where we could keep both Peloton and the Kubernetes platform running at the same time and continuously start moving stuff both to Kubernetes, but also if we found problems with services, back to Peloton without much pain. So the concept we came up with for this is service portability. And it's the idea that you can take services and their workloads and decouple them and make sure they don't have dependencies on the underlying hardware and scheduling system. Now, this can be really quite annoying because this is something that you do have to talk to service owners about. And it took a lot of time. It took over a year to get portability to a state where nearly 100% of services were portable. But it is incredibly useful because it is incredibly useful for migrations like this and for other reasons which I'll get to. So portability, there's really two parts of this. There's movement tolerance, as in the system is not dependent on the scheduling software it's on, so you can both onboard it from Kubernetes and offboard it from Kubernetes without impacting the service and the workload. And also distributability. In portability, services are not dependent on being in certain network groups, in certain availability zones, or on certain hosts, and so you can reduce risk by distributing services across different zones. The other thing, though, you can do as well with this distributability is you can distribute services across different scheduling software. So you can have a service on Peloton and Kubernetes at least temporarily at the same time. So this is portability, and this is what our system looks like roughly. So we have, I updated these numbers today. There's a lot more Peloton clusters on this diagram than exist today, but we'll get to that. But we have 57 clusters, 24 availability zones. These are our own availability zones, but they roughly map to cloud provider zones, on-prem data centers, etc. And 4 regions, most of which is the US. There's also a region in Korea because of the data privacy laws where you have to keep data in country. And then, so 22,000 hosts, 3.4 million CPU cores, and then it's the platform is broken down into regions. Each region has multiple zones, and each zone can have one or more Kubernetes or Peloton clusters. So to rebuild our platform to work with Kubernetes, we already had this system called a backend, and the idea of a backend is that it takes this abstract goal state that I spoke about before, that our users request us to place, and it turns it into commands to actual compute clusters. So previously we already had a Peloton backend that created these commands for this Peloton system that created containers. And so we just slotted in effectively the Kubernetes backend next to that. And for some of the stuff where we wanted to keep the experience the same as Peloton, we built our own CRD that then overloaded on top of it overloaded on top of the deployment CRD. So with a lot of the same behavior as that one. But that is not just the end of it. There's a lot of challenges to doing this migration, even if you have portability and even if you have this platform. So you've got risk, you've got performance of reads, and you've got some of the features that engineers at Uber are used to that you need to keep. So first off, risk. We did not want to, through this migration, move a critical service to Kubernetes and blow up the critical service. So how do we do that without actually completely moving the service? So in some other companies and in some other processes I've seen before, there is an expectation that the main line of the repository very quickly reflects what is actually running across 100% of production. And that is great because you get immediate feedback on your change and etc. But it's also not great because if you apply a bad change, you get immediate feedback when your whole service goes down. So we use a more gradual approach to pushing changes through the deployment system. What happens is that our users, as I said before, give us their goal state. They tell us how much CPU and RAM they need, where they need to be placed across the fleet. And also, if they have special permission, they can ask for a few things like special hardware. We look at their actual state across all of our Kubernetes clusters and also our Peloton clusters as well. And then from that, we diff out what is different between what they've requested and what they're actually running right now. And those become a set of required changes. Those changes are turned into steps that form a rollout plan. So each step might be, for example, that in this cluster, we need to update your deployment spec. And each step also has a completion conditions called gates. So in this case, for example, the completion conditions are that the container is deployed successfully, that the service-wide alerts do not fire, and that there was at least a 10-minute wait so that if the alerts fired 2 minutes in, you wouldn't just have moved on by that point. So this is what that actually looks like in the production system. You can see the first three steps here are completed, and then this fourth one here is in progress. It's updating a deployment specification on a compute cluster called Phoenix 6 Kubernetes stateless 01. And once it's done that, it's going to monitor the alerts. It's going to wait 2 minutes, and it's going to do this thing called UNS. UNS is basically checking that containers are reachable across the system. So is the container actually healthy and serving? And so with this system and with this gradual change, gradual but automated change to the production environment, you apply the first step of your broken change, the gate for it, so that container is healthy fails, and then you have to roll back. So rollbacks just look at the tasks that have the steps that have already executed or began executing, and it generates corresponding rollback steps for those. That's by snapshotting the state of the system at the point at which you started this deployment, and then using that as the goal to get back to. So you can see for some of these where it's upgraded the it's updated the Kubernetes deployment spec. It's now doing a corresponding step that's going to update it back to the old configuration across those clusters. If you had added this service to a different Kubernetes cluster, there would be a corresponding step to delete it from that Kubernetes cluster. Normally, this is good enough. Obviously, not every service is healthy when it goes back. That's not error-free. 90% of the time it is. 10% of the time it becomes a bigger problem. But the important thing about this is in that 90% of the time, no human has really had to get involved here yet. The system tried to move it couldn't, it rolled back. Maybe someone will look at this in a few hours. It's not the service is down moment. So that's one thing. So here we are. So here's the rollback step, apply to previous service version, and we're back to green. So another issue we had with the platform was another issue we have with the platform is we wanted to make sure that we didn't break our most critical services as part of this migration first. So we have a concept called tiering. And tiering is how we measure how important a service is to the platform. So in tier 5, we have services that nobody really cares about. There's a bot that runs a foosball league in tier 5 in our office, for example. All the way down in tier 0, you have services that if they break, the Uber app does not work globally. And so if that happens, people can't go online, people can't get rides, people can't drive and earn a living. It sucks, right? And one of the ways we de-expose this migration, but other changes too, is we run through these migrations from the highest tier services first, who effectively become the guinea pigs and the places where we soak the integration. We found quite a few bugs in tier 5 and 4, but because we rolled this on a tier by tier basis, it meant that when we found bugs that might break a service, it didn't really matter. Because yes, your internal foosball league is down, but who cares at the end of the day? It's not like the Uber app is down. And that was really useful because it's very hard to identify all of the places where something could go wrong until you actually do it. But by doing this, you can at least select candidates who are more suited to being those guinea pigs. And this is one of the things that maybe if you're not doing today, I know that portability is a huge effort. I experienced it myself, and you probably won't be able to do that very quickly. But tiering, if you don't have it already, or at least having an idea of what of your services are the most important versus what aren't, is pretty easy to set up in terms of defining it. And you can use it not just for migrating to Kubernetes, but for any other configuration change you make to your platform. We use this all the time when rolling out new features to our platform. And we're using it right now, for example, as we're onboarding services to using ARM CPUs, we're going tier by tier because it reduces our risk, because we're more likely to find bugs in these higher tiers. So yeah, so we rolled through the migration tier by tier. So we started with tiers 5 and 4, nobody cared. Tier 3, which is like the support, the web panel for the support team, and then tier 2, the first customers-facing services, and then through 1 and 0, which is the actual core trip flow. And by doing it this way, we had quite a lot of confidence by the time we got to tier 1 and tier 0 that we weren't going to find anything unique that was going to break. So that's de-risking. The next thing, these slides are out of order. Anyway, the next thing is container snapshotting. So Uber engineers are quite used to having the ability to snapshot containers because Peloton supports it natively. They want to be able to take a container that failed, download the snapshot of the file system, and inspect that to try and debug what went wrong. Now, in Peloton, that's really easy because Peloton doesn't clean up after itself, a lack of a feature that turned into a feature. On Kubernetes, though, it's actually more of a responsible citizen, and it cleans up for itself pretty quickly. So we had to deal with this. So what we ended up doing is we added a tiny sidecar container to every pod that we execute, and that sidecar container waits for the waits for the main container in the pod to exit. When it does, it stops the deletion process. It takes a copy of the file system of the main container and uploads it to this blob store called TerraBlob, but any blob store would do, S3 would do, GCS would do, etc. And then it just makes a reference to that in an internal registry. And so by doing that, the snapshot remains available. And then engineers can, here's the sidecar container. So here it is. It takes the shared volume from the main container, uploads it to the uploader, and then you can see it in the platform. And then engineers can go in and they can see, for example, this is a snapshot of a service that crashed called Access Decider in the production environment. So that's how we solve for that. And here we are. So, and the other issue we had to deal with was read performance. Up is a huge platform, and a lot of the requests it makes are quite necessarily like fanned out requests. So if, for example, I need to make a change to your service, but I don't know what clusters you're running in, I have to check every single cluster to see where your service is and what state it's in on that cluster. And we found that the request rate we were doing, I can't remember the exact numbers, but it was in the tens, hundreds of thousands. It was far too much for Kubernetes to handle, and we were going to stress the clusters far beyond their limits. So what we ended up doing here is we ended up using an in-memory data store, almost like a cache, to get this information, and then those caches were being fed by informers on each cluster. Now, that does mean that this system is eventually consistent. Obviously, etcd is a fully serializable system where you're guaranteed that if you get a result, that reflects the head of the cluster right now. On an informer, that's not guaranteed at all. You might get an update a second, 10 seconds, a minute after it actually arrived. So how do we deal with that? Well, in our case, we just use time as a synchronization primitive. So time is also not perfectly in sequence, but it's perfectly in sequence enough. Our NTP guarantees are, I think it's 0.1 seconds for the 100% of the time is what the NTP folks at Uber guaranteed us. So there we are. But so we look at the date that Kubernetes saw the change at, and then we use that to tell whether we can take your request. So you might say to us, show me all the information about this service across all clusters, and the timestamp that is the minimum I want to read is like the timestamp now. And it may be that if the informers are really delayed, you might have to wait 10 seconds or a minute to actually get this data back from the system. But the data you get back will be at least at the timestamp that you asked for. It might be in the future of some clusters, but at least it will not be data that came from the past. So if you just made a change and you're looking to see what the effect that change had, you can at least see that, and you won't see the system before. So now I have a demo of moving from the Peloton system to Kubernetes. This might work, it might not. For context, we've migrated so much now that there were no compute clusters without Kubernetes running on them that I could find space in, so I had to provision one that's just connected with a note saying, please don't remove. But we'll see. So over here, I have a service on the Up platform. I need to close all these. I have a service on the Up platform, and it is currently running on Peloton. So if I go in here, you can see this is what Peloton looks like on the front, and it's running these two tasks here. And I want to move it now to Kubernetes. So I'm going to go over to my terminal and run a command to force it along. Normally, we would just be automatically trying to push you forward to Kubernetes, and then if you got rolled back, we would go and look. But I'm just going to force the issue. And the way I'm going to do that is I'm going to run this command, which I doubt you can see, it's kind of small. But what it says is it says up compute set placement -s my service name -e my environment name -k placement kind default Kubernetes only. I'm going to execute that, and like I said before, this is going to generate a rollout. It's going to look at my actual state and the state I just asked for. So the change now is that I asked to be placed on Kubernetes, not Peloton. It's going to work out the difference, and the difference in this case is I'm on Peloton, I need to be on Kubernetes. Is this running? Sorry, I'm using the wrong one. I need to change my environment name because I messed up the command. So if I just change this to staging, then live demos. Here we go. Cool. So now you see I have, it took in my goal state. My goal state was to be on Kubernetes. It looked at the actual state. The actual state is my services running on Peloton. And it worked out the required state was to create instances on a Kubernetes cluster and to remove instances from the Peloton cluster. It's now going to try and do that. It's going to create instances first because we have a policy called make before break, where we will always create your new services before bringing you down so you don't have downtime. So it's going to try and do that. Once it's done that, it's going to try and look up and see if the containers are there in this thing called UNS, which it hopefully should do relatively quickly. Yep, and then after that, it's going to delete them from Peloton, which if I refresh here, I should be able to actually see. Yep, they're being killed. And in a few seconds, it should... Is it going to do it? Is it going to do it? Oh, they're gone. Yep, cool. And it's migrated over. Cool. So that's actually how a migration looks. If something had gone wrong, it would have rolled back, and then someone might take a look and see what the heck's going on. Yep. So good. That demo worked. I don't have to use the. I don't have to use the video. Yep. So oh no, I don't want to play the video. So what did we learn? So Kubernetes, as kind of Kelsey said in the talk earlier, does not just solve all your problems. It's a tool. We had to build a lot of stuff that wasn't in stock Kubernetes, primarily not because the stuff in stock Kubernetes wasn't great. It was, but because we didn't want to do a sea change of how things worked for our engineers. We wanted things to stay at least relatively familiar to them in how Peloton, on what, for example, what environment variables they get from Peloton versus Kubernetes. But the flexibility of Kubernetes and the minimal API it gives you is a strength of it, because it means you can define pretty much anything in there. And so if you've got these unique requirements that maybe no one else has, that's fine. Just write an operator for it, and you're good. So yeah, that lack of opinion is extremely powerful to us. We don't just use Kubernetes even for just workload and service execution. There are some teams now in Uber that are using the Kubernetes operator pattern exclusively to apply state onto external systems because they just like the pattern. So for example, I believe there's a team called the Service Lifecycle Management team, and they have a Kubernetes cluster that just has an API server and etcd and no nodes at all. And they are just using that to push forward service state using the operator pattern. So yeah, that's useful. And the other thing, like any migration, yes, the first million calls are the easiest. And that's because, at least in many of these migrations and changes, we found that there is a long tail of services that are particularly special or unique, and they are the ones that are going to be a huge pain. And it really is that 90% of your time will be dealing with the 10% of services that have done something special. This is why also I think it's really important that when you build a platform, you're very deliberate about what configuration options you give your users and why they're valuable. Because if you're not, and if you give users the ability to configure absolutely everything about their workloads, you will find people doing things that might surprise you, might make your life difficult in the future. And so it's really important, at least to me, that when we give users the ability to change parts of their configuration, that we have a good story for why we're doing it and a good story for how we're going to maintain it in the future. An example of that we have is the volume mounting, which we've before in the pre-Kubernetes system. Some people were doing some really weird things with NFS, some really weird things. But nowadays, if you want to even use NFS, there's only a few ways you can use it, and you have to have permission, which we're generally not giving out, especially to new services, because we have an entire database as a service system that they really should be using instead. Yeah, so as of right now, this graph is out of date. This graph says 80% of the fleet. It's 100% because that was the last service, because as I said, I had to put a Peloton cluster up to move it. So yeah, so right now we're at 100% done. Yeah, our largest clusters are about what it says there, 5,500 nodes. It becomes, things get a bit weird after 5,500 nodes, especially when you've got a lot going on, a lot of events flowing through the API server. So we're probably going to call it about there and just go out horizontally rather than vertically from there. Yeah, that's where we stand on our migration. So that was our stateless fleet. And now we're looking at moving more stuff. So our batch and stateful fleets have something like 6-7 million cores that go extra. So we're looking into whether and how we want to move those. I believe there's a team in the stateful side who are doing some proof of concepts for how they're going to do that. Nothing yet, but I'm sure they'll give a talk one day. And yeah, that is it. If you've got any questions, I'll be happy to answer them. First thing goes to a blog post about the Up platform, and then the middle one goes to a KubeCon video about the actual Kubernetes clusters themselves and the modifications that have happened on there. And then the third one goes to Uber Denmark's website, if you care about that. Yeah, thank you.
All right, excellent. Thank you so much for your talk. I always heard 80 versus 20, but 90 versus 10 sounds more applicable. We're getting some questions in. Yeah, let's go for the first one right away. How do you design clusters for that scale? What's the size of your clusters?
Okay, I hope that the last slide was useful for that. But generally, yeah, we don't go above 5,500 nodes. One of the biggest issues that we have with clusters right now is resource fragmentation. So if you have, say, 2 CPUs free on each node, and there's 5 nodes, and you want to place a service that needs 8 CPU, you can't place it. Despite, from an outside perspective, you look at the free CPU, and there's 10 free. We've been doing some stuff with bin packing to try and improve that, if not really for the main stateless fleet, but particularly for GPU services that use H100s. It's really important because we don't want to have many of those free because they're really expensive. So I hope that's useful. But if you want to follow up with that, like more specific pointed questions, feel free to throw them on there because that's, yeah.
All right, follow-up questions, welcome. Good, next one. How long did it take you to build all the tooling required to migrate the apps over to Kubernetes?
So the actual migration itself, outside of portability, ran basically through 2023. And by the end of 2023, we were pretty much there. In terms of what we actually had to build, obviously the back-end change had to be made. And then outside of that, it was mostly emulating some of the features that existed on Peloton that didn't exist on Kubernetes, because by doing that, we didn't have to go and talk to service owners and say, we need you to change this, and this, and then they say, sure, come back to us in 2 years, which happens a lot when you talk to service owners.
Funny that.
Yeah.
All right, just allow listing a couple of them. Give me a second. Only one person, sorry, people. All right, I feel like that might not be the right one. Are you using any progressive development tooling?
No, a lot of it is unfortunately proprietary stuff. We have our own continuous deployment flow that's built internally. A lot of this emulates stuff that is open source, and my personal opinion is we should be using more of it. It's just a lot of this just comes down to that we built it many years ago, and now it's a thing of I think sometimes doctors say we don't treat things that are healthy, sort of thing. But I wish we could.
Cool. I'm going to ask this one because I'm pretty curious. What was the most interesting challenge bug you faced during this migration?
We had one service, I think it was called Spark Remote Shuffle or something, where it turned out somehow the service owners had managed to get it deployed on Up and had managed to block Up from moving or restarting it for over 6 months. Because the moment you tried to start a new container of it or stop a container of it, the whole service crashed. So we tried to move it to Kubernetes, as said before, and it tried to create clusters on Kubernetes. And when we created clusters on Kubernetes, it crashed both the containers on the K8 cluster, but also somehow crashed the containers on the Peloton cluster because of some contention. So then we roll back, and the Peloton ones start crashing too, and then we get alerted because we can't even roll back the service. So we end up in this state called abort, where you're just halfway between. And that one was... it landed on the service owner, but that one really was a pain to move. I think it was Christopher, our office, spent like 10 hours just watching it really slowly move. They just added a huge waiting gate on it, and eventually we got it over, and we told the service owner, if this now crashes on Kubernetes, not our problem.
Aside from that, any interesting human problems?
Obviously, whenever you go and ask service owners for something, they have understandably a lot going on, and so they really don't want to move. And it can be very, in fact, with portability in particular, it can be very difficult to get the buy-in. So you really actually do need the leadership or cultural buy-in to actually push something like portability, and also when you have service owners where there's problems with migration to push this forward, because otherwise if you don't have this buy-in and you try and do a migration like this, you will end up with 1% of your services left behind that you can't move. And now you've gone from, I think there's an XKCD about this where they're like, oh, this solution sucks, we now need an extra solution. There is now one more solution to maintain. But yeah, that is yeah, that's my view on this.
Perfect. Let's do one last one, and then we'll go into a break and also a sponsor showcase that you should definitely visit all of these sponsor booths. I'm obliged to say this. You mentioned that you don't use Kubernetes deployments. What's your alternative approach?
I may have misspoke there. We have the behavior of our deployment system, which is quite literally just called Uber deployment. It's very similar to the Kubernetes deployment one. It's just overloaded with some stuff that the deployment one doesn't have. What was it that it was? I think it was some stuff about tolerations and disruptions, and I think there was some stuff about sorry, I can't remember now, but I can look after if you want to come up to me. But yeah, it's very similar though to the deployment object that you're familiar with in Kubernetes. That was it now. When you scale a deployment say you're scaling it from 20 containers to 2 containers, that is not considered disruption by the deployment object. So you will just go 20 containers today, instantly 2 containers, 18 are killed. And we found that some services didn't like that because of the way they were interacting with like databases on the other side, that they had to shift responsibility around. You might say that's not stateless. I would agree. So we had to do a gradual scale up, scale down when we changed the desired replicas. And that was one of the big things as to why we ended up having this overloaded CRD that had that extra feature on top.
Cool. Thanks. Let's do one more round of applause for Lucy. And happy break.